In this video, we will create a map of co-prime pairs. Basically, if the pair xy is co-prime, then we place a dot there. If not, then we leave it blank. And from this map, based on the pattern formed by the number x, we can deduce if x is a prime number or not. Also, we will define a new parameter, primeness of a number in abstract sense. Whether a number is prime or not prime, it has a very true-false kind of answer. However, for a non-prime number, we want an answer here to how close it was to being a prime number. Can we make a scale on which we can compare the primeness of numbers, where value 1 means perfectly prime? And then we can easily take two numbers and say that one is comparatively more prime than the other one. Before visualizing the patterns, let us start from the basic question. What are co-prime pairs? Some of you might already know that the co-prime pairs have no common factor other than 1. Or in other words, we can say that if the greatest common divisor, which is also known as the highest common factor of two numbers, is 1, then they are a co-prime pair. For example, take the numbers 14 and 25. Individually, they are not primes, but they do not have any common factor other than 1. Therefore, they are a co-prime pair. How to compute that if two numbers are co-prime or not, or check if their SCF is 1? The trivial way could be doing the prime factorization of each number, which we did for the previous example. But that was an easy set of numbers. What about 273 and 483? There is a comparatively quick method which I found in the chapter 10 of Vedic mathematics book. Let there be two numbers p and q and their SCF is h, and a and b are the quotients we get after dividing by the SCF. We can add or subtract p and q, still the common factor h remains. Not only that, we can also take any multiple of p and q. It still does not affect the common factor h. Therefore, the SCF of p and q is same as the SCF of p plus minus q, 2p plus minus q, or in general mp plus minus nq. Let's see it with the example of 483 and 273. Subtract the 273 from 483, we get 210. Now subtract 210 from 273, we get 63. Here is the tricky part. We can subtract the multiples of 63 from the 210. To be exact, 3 times the 63. And after subtracting, we get 21 as our next number. Now it's clear that 63 is evenly divisible by 21. Therefore, 21 is the SCF of 273 and 483. We can also verify this with the prime factorization method. By closely looking at the series of numbers we got here, some of you might have already identified that we will get exactly the same numbers if we use Euclid's division lemma to calculate the HCF. Now we have all the tools required to visualize co-prime pair patterns. Let's plot it for 20 by 20 grid on x and y axis. As expected, the patterns are symmetric about the y is equal to x line because SCF of x and y is same as SCF of y and x. So let's just remove the top left triangle. Identifying a prime number from this pattern is very straightforward. Basically, if all the dots in the pattern of a number are placed with no gap between them, then it is a prime number, because that number is co-prime to every number smaller than itself. We can see that for all the prime numbers here. Now look at all the non-prime numbers. Some of them have dense dot patterns, while for some the dots are sparsely placed. Based on this observation, let's define the primeness of numbers. For a number n, primeness is defined as number of dots in the pattern from 2 to n minus 1 divided by n minus 2. Let's plot the primeness of first 50 numbers starting from 3. Clearly all the prime numbers have a perfect primeness of 1. But among the non-prime numbers, we can see that the number farthest from being a prime number is 6. Also 30 has the same primeness. Also you will notice that the curve follows this zigzag pattern. It does not go up and up for consecutive numbers, neither there is a repeated decrease. Even for a large set of numbers we see the same behavior. Why is that? Let me know in comments what you think of it.